Molecular orbital theory. So let's go back a little bit and see what we learned when we first really talked about orbitals, the term orbitals and electrons. So in the quantum mechanical model, we learned that an orbital is the volume that takes over around 90% of the probability of where an electron is likely to be found, right? So we learned an orbital is a high probability of where an electron can be found. A region of space with, let's say, a good chance of 90% probability of where an electron is likely to be found. And now here's the key. When modeled as a standing wave around the nucleus. Remember that electrons can behave as particles and waves. Particle-like behavior we explained through Lewis theory, Valence theory, because we're thinking of just the electrons bonding. Now, we know that through interference and different experiments done, electrons create patterns that are very similar to wave-like behavior. So the quantum mechanical model created the orbitals to say that the orbitals have the region of space where these electrons are orbiting around them, because they don't just act as a particle that's in one specific spot. Now, if we're just looking at the wave-like behavior, we're looking a little bit more specifically into molecular orbital theory. These orbitals that were discovered in the quantum mechanical model are based on solutions from the Schrödinger equation. Now, in molecular orbital theory, what we want to do is we want to delocalize the electron by modeling them as standing waves around multiple atoms in a molecule. So we're not just trying to look at a single atom like we do in valence bond theory. We're trying to look at the entire molecule. So in MO theory, we want to delocalize the electron by modeling them as standing waves around multiple atoms in a molecule. Creating molecular orbitals. So this is all, nice if we could do that, but it's actually almost nearly impossible to solve. So we do something called trial functions, because it's very, very hard to actually solve this. An example would be, what if you had a really complicated math problem? If you had x to the power of 6 plus 2x5 plus 4x4 plus 95x3 plus 2x2 plus x plus 90 is equal to 0. Now, you can solve this mathematically, or what you can do is you can make something called successive approximations. You can just constantly guess a little bit. All right, I think x is this. Does this give me the answer of 0, etc.? Now, that is what we do with the Schrödinger equation. We guess what we'll substitute in for the Schrödinger equation to give us the answer. So in MO theory, that little guess, so our successive approximations, are called linear combinations of atomic orbitals. In valence bond theory, we created hybrid orbitals by combining standard atomic orbitals on a single atom. Now, this doesn't apply here because that just explains the shape of the central atom and the bonding. Here, with linear combinations of atomic orbitals, we're creating molecular orbitals by adding together standard atomic orbitals from different atoms in a molecule. So there's the difference. We know valence bond theory is creating hybrid atomic orbitals, combining standard atomic orbitals on a single atom, where the molecular orbital theory is based off of the linear combinations of atomic orbitals that come from adding together, not combining. There's the one already big difference. Valence bond theory is the overlap that shows you the bonding to give you the shape. This is adding together standard atomic orbitals from different atoms in a molecule. Now, let's look at that a little bit more. Here's a little picture. I'm going to actually move this up and make it bigger. So we know that waves can act constructively and destructively because you can have a wave that goes both in phase to make you a bigger wave, or you can have waves that go the other direction from one another to cancel out. So this kind of explains it here. So, for example, let's look at constructive interference first. If you have two s orbitals that are going to combine, that's why we say plus, they will have constructive interference. They're both in phase. And what we're trying to explain with that is, remember that we don't know that an electron is always going to be at that spot. It could be in anywhere, since it has wave-like behavior. Because of that, we have to look at both of the ways that they can interact. So they can have bonding, where the two can combine to form a nice big orbital, which would be that standing wave. And since it's a direct head-on collision to make something bigger, we say that's a sigma 1s molecular orbital. Now, this has a higher chance of finding an electron. If we think of a little picture, and you have, for example, if we draw an axis through these two atomic orbitals, and you have your one wave here, and you have your other wave here. Now, because they're in phase, they're going to combine to form a bigger amplitude. Now, remember, the amplitude was the height. That's kind of what this orbital represents right here. So the increased amplitude of the wave increases the probability density. And remember, the probability density is the solution to the Schrödinger equation, psi squared, which gives us a greater chance of actually finding an electron. So because you can see here how the waves are in phase and connect, they then combine to form an even bigger wave. And that bigger wave is that molecular orbital, which gives us an even greater chance of finding an electron because of the increased amplitude. Now, would you think that all of this great stuff here would make this higher in energy or lower in energy? This would be lower in energy because having a greater chance of finding the electron stabilizes the molecule. So sigma 1s molecular orbital will be lower in energy than the atomic 1s orbital. Now, once you've combined those atomic orbitals, those no longer exist, and you only have the molecular orbitals. So that's bonding. Let's look at antibonding. Antibonding would be if you have destructive interference. So you can have waves that are not in phase. So if you had an electron, if I drew my axis here again, and I had one wave just like before, and then the other wave went the other direction. Now what would happen here is they would actually cancel out, forming a node. It's like they're subtracting from one another because they're out of phase. That's destructive interference, and we call that forming an antibond. Now you can see here, this is a sigma 1s star. That star representing, this is actually antibonding because of different destructive interference. Now the amplitude decreases here. Which decreases the probability density and therefore there's a node between the two nuclei. This is your node. And we have a less likely, I should say, chance of finding the electron. So this will then be higher in energy because it is less stable. Now, for us to determine whether a molecule has bonding or antibonding, we always include both and fill the electrons with rules that we've learned previously to look at how this molecule is stable or unstable. Since the other representations have been more of simplified versions to see the stability. Let's look at an example by actually drawing something called a molecular orbital energy diagram to show the difference. So if we look at H2, and I draw an MO diagram, I draw the atomic orbitals of hydrogens on the outer sides of the molecule. So I have one S and one S, one electron in each. Now I know that the 1s will have constructive interference. So I have my sigma 1s star and, I have my sigma 1s, that's lower in energy. Then I have to also write my sigma 1s star because then combining the electrons will tell me whether I have bonding or antibonding orbitals and whether I am stable or unstable. So then all of the rules apply here when we were filling in atomic orbitals as molecular orbitals, meaning you first fill the electrons in the lowest energy level with spin up and pair before you move to the next energy level. Here now we have our 2 electrons and we're finished. So this molecule only has bonds and electrons in the bonding orbitals. Now, another way to look if this is stable or not is through determining the bond order. The bond order shows us exactly how many bonding to antibonding electrons we have. It is equal to the number of bonding electrons minus the number of antibonding electrons divided by 2. So here, I have 2 bonding minus 0 antibonding divided by 2. 2 divided by 2 is equal to 1. We look at bond order to be when it's a positive number, it's pretty stable. And if it's 0, it's likely not to form. The higher the bond order, the stronger the bond. So we know a bond order of 1, if we look at the structure of hydrogen, that's a single bond. So that's stable, but we know that, for example, a double bond, a triple bond, a shorter bond length is even stronger. Let's look at some different examples, more going through molecular orbital theory. What about He? So let's move on to a different page here. Let's say we had a diatomic helium. So again, energy, orbital diagram, helium on both sides. You have your 1s. This time you have 2 electrons in the 1s. And you have your sigma 1s star and sigma 1s on the bottom here for lower energy. So you then fill in all your electrons applying to the same rule. So you take 1 electron from here and 1 from here. And then once you paired your bonding, then you would move to your antibonding. So 1 and 1. So now you've used your 4. Another way to always double check is because this has 2 valence electrons and this has 2 valence electrons, the individual helium atoms, the molecular diatomic helium should have 4. Now, creating the molecular orbitals does not necessarily lower the energy of the entire system. This is a great way to find the stability through bond order. So does diatomic helium actually exist? Bond order here would be 2 minus, we have 2 in antibonding, divided by 2. 2 minus 2 is 0, divided by 2 is 0. So this is not stable. This would not really exist. What about helium 2 plus? This plus means that one helium has lost an electron. Doesn't really matter which one. So if you have your 2s and you have the 1s, and the other 1s has lost the electron, you have your sigma 1s and sigma 1s star, just like before, and you fill your electrons one at a time. Now you have one less electron, and the reason that you'll see those dotted lines is that just so you can see which linear combination made the molecular orbitals. Now here you see, all right, well, is this more stable? Does this exist? The bond order will be 2 bonding minus 1 antibonding divided by 2, which gives you 1/2. Well, this is not 0, so this is more stable. So diatomic helium can actually exist if it's an ion. Valence bond and Lewis can predict that helium 2 plus can exist. But molecular orbital can actually help show you that it can actually exist. So that's the importance of molecular orbital theory. It helps explain the existence of some molecules, what valence bond and Lewis theory actually can't explain. And there's a little bit more of an example coming with that shortly. So this is just talking about our s orbital combination. Now, most of the time we have more than just the s orbital combinations. What if we get to the 2p? So we know we have 3 p orbitals. We have our px, py, pz. Now, if you take those with linear combinations as well, again, you will have bonding and antibonding. Now, the p's will form actually different ones. Because px is along the axis, it can only combine once and form a sigma p orbital. The py and pz, because they're up and down of the axis, they can combine twice, overlap, to form pi p bonds. So for your p orbitals, you will form a sigma p and 2 pi p always, because you have only the 1 collision for the px and the 2 for the y and the z. Now both of these will form the antibonding and the bonding, just like if the electrons, for example, for your px, if your electron was right here, they would overlap to form your sigma. Now, if they were out of phase, they would then not completely form with the node in the middle, just like before. So you can have sigma p star, pi p, and pi p star. Now, sigma, because of that direct head-on collision, is actually usually lower in energy than pi. However, the way that we distribute the pi orbitals is a little bit different for certain molecules because of something called sp orbital mixing. Now, before I get a little bit more into that, let's look at the first generic way of writing the molecular orbital diagram. So let's look at oxygen, O2. Oxygen has 6 valence electrons and wants to bond twice. We know O2 looks something like this. Now, the interesting thing with oxygen and why I use it as an example is because when you place liquid oxygen in between a magnet, what actually happens is that it doesn't flow through. It becomes attracted to the magnet and kind of stays. So let's say that you have a magnet here and here, and you pour liquid oxygen through it. Now you would assume that it's going to go all the way through because right here you can see all the electrons are paired. But what actually happens is the liquid oxygen stays between the magnets. This would mean that there's some electrons that are not paired that attract to the positive and negative ends of that magnet. This is another example of where molecular orbital theory helps explain the actual molecule rather than valence bond and Lewis theory. So if we look at the energy diagram of O2 to help explain the magnetism. So again, remember, diamagnetic is when you have paired electrons, and paramagnetic is when you have unpaired. Paramagnetic means that the electrons of that are unpaired become attracted to an external magnetic field. So this means that oxygen is actually paramagnetic from the example that I'm describing. But it does not look paramagnetic from the diagrams of Lewis and valence bond theory. So if we draw the diagram, we can see, all right, I have oxygen, and O2 in the middle. Now I know I have my 2s. Note that I'm not writing 1s because we're usually just looking for the valence shell because those are the ones that are creating the molecules. We have our 2p. Alrighty, so 6 in each, so the total molecule should have 12. So we have sigma 2s and sigma 2s star. Nice and simple. Those will fill up completely. Now the trick here, I'm actually going to move this down a little bit to have some more room, is the placement of the p orbitals. So sigma is lower in energy than pi. It's more stable because of that direct collision and that direct combination. And that there's a lot of electron density right there in the middle. It's not too much distributed like the p's. So sigma p comes first. Sigma 2p is lower in energy than pi 2p. And then the sigma antibonding is also less stable, so pi 2p antibonding comes first before sigma 2p antibonding. Now, what you do is you fill in your electrons, one from each. So you take the one from here, that's gone, and you take one from here. Boom, that's paired. Now you move on to pi. Take one from here and another one from the other oxygen. Take another electron, you pair, and another electron. And then you have one more electron that goes to the antibonding and another. So here's the key right here. These two unpaired electrons in pi 2p antibonding explains the paramagnetic behavior of oxygen. This is why oxygen is actually paramagnetic and not all the electrons are paired. Another way to look at this is to write the molecular configuration. So that just says what orbitals you have and how many electrons. So for O2, we would write parentheses sigma 2s, and I have 2 electrons in it. Then right after that, I have sigma 2s star with 2 electrons. Then I have sigma 2p with 2 electrons, pi 2p with 4, and pi 2p star with another 2. So that's the configuration of our molecular orbitals. Very similar to our electron configuration, but we're using molecular orbitals rather than atomic orbitals to say how many electrons that we have. Now let's calculate the bond order to see if this is stable or not stable. Bond order would be the number of bonding electrons. So I have 2, 4, 6, 8. 8 bonding minus 2, 3, 4 divided by 2. 8 minus 4 is 4, divided by 2 is 2. So this is pretty stable. Now, actually talking about the difference of when you have not sigma 2p first and pi 2p first. This happens in diatomic period 2 elements, or molecules I should say, that have an atomic number less than 8. So we have the sigma before the pi when atomic number is greater than 8. Because they don't have sp orbital mixing. So when you have atomic number less than 8, for example, the boron, carbon, nitrogen, there's sp orbital mixing, which rearranges the sigma and the pi. And let me explain that a little bit more. Sp orbital mixing occurs when molecular orbitals of the same symmetry formed from combinations of 2s and 2p atomic orbitals and are close enough in energy to further interact. So, if you look at the difference between nitrogen and oxygen for 2s, that pair of electrons in the oxygen increases the energy and it's further to the right, whereas nitrogen has less energy and less of an atomic number. Now, what happens is that because of the sp orbital mixing, the sigma 2s can combine with sigma 2p, but they don't want that. So to avoid that, they kind of push further away from one another. And that push then changes the rearrangement. So if you look at just the arrangement of the p's, this is our original arrangement. We have the sigma 2p, pi 2p, and yet the sigma 2s star on the bottom. Now, because of sp orbital mixing, these can interact. So they push further away, and that sigma 2p becomes higher in energy, and the sigma 2s becomes lower in energy for those other diatomic molecules. So for nitrogen, it would look like this. You have your pi 2p first, and then your sigma 2p. But it's not just because we say it, it's for that reason. Since for those particular elements, the 2s and p orbitals are so close in energy, they can have mixing. And the sigma 2p and 2s can actually combine, and we don't want that for the molecular orbitals. So what happens is that the energy of the sigma 2s is lowered and the energy of the sigma 2p is raised to give a different orientation and a more stable structure. So let's draw the molecular orbital diagram of N2. So we have the 2s, P. Note that they should always be in the same energy distribution of both atomic orbitals. So then we have the sigma 2s and sigma 2s star. And now, because it's not oxygen, fluorine, or neon, it is nitrogen, then we have pi 2p first, then sigma 2p. And still pi 2p star and sigma 2p star. This arrangement doesn't change because the energy, even though they're pushed further away, it didn't affect the orientation of the antibonding. Then here we draw our lines to show how the molecular orbitals were combined with the atomic orbitals, and you fill in your electrons. Take one from here, then you pair, and then you take another one and another one. So your bond order is 1, 2, 3, 4, 5, 6, 7, 8 minus 2 divided by 2. 6 divided by 2 is 3, so very stable. Our configuration will be sigma 2s, 2 electrons, sigma 2s star, 2 electrons, pi 2p 4, and then sigma 2p 2. So if you wanted to just look at the configuration, figure out if it's stable, paramagnetic, or diamagnetic, it's too hard to do that just looking at the structure. You would have to draw the molecular orbital diagram because it actually explains that behavior. Now here in dinitrogen, nitrogen gas, we have all paired structures. So this is a diamagnetic molecule. Now, one more thing I want to talk about is what happens when you don't actually have the same configurations. When if you don't have the same molecule, what if it's heteronuclear? So last little bit, and I know it's a lot, before we finish with this video, let's talk about heteronuclear, meaning still just 2 for now, just 2 elements, but they're not the same. So let's do OF. Now note, there are certain rules that apply, but these are trial functions of mathematical representations, and for some heteronuclear, the arrangements can actually be more like the nitrogen and the carbon and the oxygen. Usually, it is the more electronegative element. So oxygen and fluorine here both will have the arrangement of the sigma up in energy than the pi. So you would draw your oxygen and your fluorine. You have your energy diagram, your 2p, 2s. So they will combine to form your sigma 2s and sigma 2s star. And then now, because they're both have the orientation of sigma first, sigma 2p will come first. What I want to say is if you had something like CO, it's more of a mathematical representation, but for the purposes of our book, we look at the more electronegative element going towards the lower energy, more stable. So that orientation will come first. So for OF, we will have our sigma 2p, then pi 2p, then pi 2p star, and sigma 2p star. You fill your electrons in. No, I think we have one more here. So let's count. I have 6 in oxygen. I have 7 in fluorine. So together, I should have 13, which I think I have too many. So 2, 4, 6, 8, 10, 12, and then I'm missing one, 13. Whoops, that wouldn't go there. It would still go in the P orbitals. Then your bond order would be 2, 4, 6, 8 minus 2, 4, 5 divided by 2, which is 3 halves. So here it is for heteronuclear. You go for the purposes of our class, the more electronegative element. Know, however, since these are mathematical combinations and sometimes based off of how close they are still with the S and the P, you can have the pi 2p orientation before the sigma 2p orientation first. So the main difference here between molecular orbital diagrams and all the other theories that we've learned is they help better explain the arrangement of how the electrons are around the entire molecule, explaining their behavior in real life, like the magnetic behavior of liquid oxygen that you can't see